In this tutorial, we will learn about how to design a Verilog code for a RAM module. So RAM stands for random access memory, in which the data can be stored at any random location. And once we have written the data, we can also read the data provided the particular address is given. So any RAM code will have two important operations. So first component is your data part. So here the bits D0, D1, D2, D3 are representing that at each location 4 bits can be stored. So this is called my data. Second important component is my address. So if you observe, I have locations from 0 to 7. That means I have total 8 locations from 0 to 7. And if we convert all these decimal numbers into binary, I can write 0 as triple zero, and 1 can be written as 001, 2 can be written as 010, and so on till 7 can be written as 111. That means for representing my this component, which is the address, which I am calling at ADDR, I need total 3 bits. And for storing my data, I need 4 bits. And for storing my address, I need a total of 3 bits. So any memory component will have two important operations. First one is the write operation, in which the data is inserted into the memory, and second important operation is read operation, where the data is just read from the memory. So whenever we are doing write operation, we need to give two things. You also need to first give the data, and you also need to tell at which address we want to write. For example, I tell I want to write at address 5 a data called 1011. So I will go to this address location 5 and I will write the data 1011, because by default no data will be stored inside the memory. Now comes the second component. So like this you can fill all the 8 memory locations, and once we are doing the read operation, so in read operation we just need to tell what is the address from which we want to read. So if I tell address as 5, I will just go to this address location 5 and I will bring out my data and I will store it in a variable called dout. So all these things I'll show you while writing Verilog code, but first understand the logical structure, in which first we need to write the data, and once the data is filled in these memory cells, we need to read the data. So let us now do Verilog coding for this. So let me open an application, and so like all Verilog programs, even this will begin with a keyword module, and you can set the language setting here as Verilog to enable the syntax, and you can give some name. So I'm giving name as some memory, so MEM, and like all sequential circuits, this will have clock and reset. Then I will take one signal to decide whether write is happening or read is happening, one signal to decide data in and my address, and one more thing to store my data out when I'm doing the read operation. So you can tell which are inputs in this. So clock, reset, and this w underscore r, and one more input is my data in. So because 4 bits are there, I declare it as 3 down to 0 d in, and one more input is my address also, but address is of 3 bits, so 2 down to 0 ADDR, and finally my output. So my output also will be of 4 bits only, because if the data being written is 4 bits, the output also will be 4 bits bytes. But because I need to store my output, I am declaring it as reg, and you can route d out here. Next important thing what we need to declare is our memory. So if you observe in this memory, you will observe that we have total of 4 bits at each location, and like that 8 locations are there. So how we declare such things in Verilog is like this. You write reg. First you write about data. So at each location 4 bits are there. So 3 down to 0. And then write the name of the memory RAM. And then you tell how many such locations are there. So from 0 down to 7, total 8 locations are there. So this is my RAM memory where all the data will be stored. But this RAM memory is neither input nor output because my main inputs are D in and address, and main output is my D out. But this is the memory which these boxes, if you find all these locations where all the data will be actually stored. And what data will be stored, that will depend upon what you give in the test bench. So hopefully you understood till here. Now we'll write our main logic. So I will begin one always block. So always at the rate of, I'll write passage of clock, and I'll open one begin end statement. So first you can always perform one reset operation because everything will be in X state. So I can say if reset equal to 1, we can make D out as 0. So I can write D out will become all zeros because it is a 4-bit number. I'm writing 4 tick binary 000. Else if, then I will perform my write operation. So if I want to perform write operation, I need to make this W underscore R symbol as 1. And because I am performing write, so data will be given inside the RAM memory. So RAM of address will be equal to D in. So whatever data is coming, it will go there. And next is else if this signal is 0, for example, that means we are performing a read operation. So whenever we do read operation, we transfer the data to D out from RAM. So RAM will now come at this side and semicolon. So this is our code, and just at the end you can write down one end module. So let me once show you the complete code. So this is my reset part. Here you can write a command also that this is my write operation, and whenever W underscore R is 0, it means we are performing a read operation. So this was my design code. Now we need to write test bench also for this. So now I'll beside only I'll write the test bench. So let me just open space of it module, and you can write it as mem underscore tb. Okay, and before only you can keep and write end module so that we don't forget it later. And now in between you can start filling all this. So we already know that in test bench, whichever are inputs, those become reg. Okay, so wherever input is there, you can just write reg, and whichever things are output, those become wire in test bench. So this part is over. Next you need to instantiate our code. So write down the name of the module mem, and then give some instantiation name like dut, and then you inside this you write the name of the signal in same order. So I'll just copy and paste here this same order. Okay, let me just yeah. So after you have done code instantiation, you can create one initial block to generate the clock signal. So how to generate is you make first clock as 0, and after every 10 nanoseconds, so hash 10, we can make clock equal to not of clock. because clock, if you observe, is always going from 1 to 0 and 0 to 1, and this we can end. So this initial block was just for clock generation. Next, let us open one more initial block for generating other signals. So initial, begin, end. So first we can write our $dump files, because these two files are essential to get the simulation timing waveform. And next thing you need to write it $dump vars. Okay, you can write 0 comma dot, and then we can write one $monitor statement to print all the signals. So here we have so many signals. So first always write down time equal to percentage 0t, and then you can print clock and reset. So clock will be equal to percentage b, and then our reset is there, reset equal to percentage b. Okay, and then what else we have? We can print whether we are doing this write or read. So w underscore r equal to percentage b, this you can print. Then you can print your d in, and then we have our address. So all I am printing in binary numbers, and after address I can print my d out equal to percentage b. And just for printing time we can write $time, and remaining all signals, clock, reset, you can just copy this same thing and write there, because I'm printing them in the same order. So it became a large statement. You can write in multiple lines also, but just I wanted to show you. Anyway, so now comes the main part. After we have written all this, now we need to start giving values. But before we give values, like every time, first you give reset signal. So you make reset as first one, and after some time you release the reset also. You make it 0, because if you maintain reset always as 1, it will remain in 0 only. No changes will happen. After this, first always remember in memory, always first we need to perform the write operation. So I'll make my signal w underscore r as 1, and now I'll start giving my different values of address and daytime. So if you remember from this, we were having total 8 locations from 0 to 7, and each location can store 4 bits of data. So at each location I need to now provide 4 bits of data, and addresses are going from 0 to 7, means 000 to 111. So because w underscore r will remain 1 only for write cycle, no need to write it again and again, you can directly give. So address I am giving this time, see, 3 tick b000, it means at address location 0. Then you provide your d in, whatever data you want to give. For example, I want to give this data 4 bit, right, like this 4 bit 111, this data I want to give. And then you can give some delay of 20 nanoseconds, so that this location 0 will be filled with data 1111. So like that, not only 0th location, you need to fill all the location. So I'll just copy this line 8 times, and then I will edit it for different addresses. So one is 01010, and then 011, then 100. Okay, then I can write 101, then 110, and finally 111, which is the 7th location. So from 0 to 7, total 8 locations are there. Like this, you can edit the data also. So just I am giving different values by changing the data. So this is, I'm just giving some random values. There is no logic to this because any 4-bit number you can fill here. Okay, like, okay, so this is the data I have given for all these numbers. So now after you have done with our write cycle, this is our write cycle. In write cycle, the data will be written to all these locations. After this, we can perform our read cycle. So before we do our read cycle, we need to make w underscore rs 0. And whenever we are performing read operation, we just need to provide only the address part. No need to again give the data part because data is already written in those locations. So if you observe this value is getting repeated, you can give some another number, no problem. Like 0101 like this, any 4-bit number. So now I'll perform my this read cycle. So just I'll copy this once. On it, you can write again also. So w underscore r, this time I will make it as 0. So this represents my read cycle. And just this time I need to just provide the address values. Based on those addresses, the data will automatically come. So let me just copy this line and I'll erase the irrelevant part, which is just this d in part. Remaining all things we need. Only the data we don't give again because data we have already given once when we are doing the write operation. Okay. So this delay just you can set properly. And after you are done with the read cycle, there is nothing much to be done here. You can just call your dollar finish and you can just run this code actually. Now we are done. So what I'll do is I'll just copy this code, design code and test bench code in EDA playground and we'll try to run this code. And if any errors are there, we'll rectify it there. So for running, you can select the tool here as this Icarus 0.9.7 and you can click on this open EPY after run to see the timing diagram. So let me once run this code. Okay, so it's asking to login. Yeah. So let me once log in and paste the code again. So once again, I can paste here the test bench and this design code. And let us again select that same tool and run the code. Yeah, so we got one error. So I just forgot here semicolon. This semicolon here was missing. Now we have rectified and now we have got this timing diagram also. So if you observe here, the signals are not in the order which we want. because in EDA playground they are displayed in alphabetical order. So you can rearrange the signals as we need. So I always prefer clock at the top, and after clock I set reset. After reset, I want this W underscore R, and then we can have address data in D out. So this is the order I want, because based on clock only everything happens in sequential circuits. And you can select radix as binary. And if you observe here, sometimes it is not showing 3 digits for this. So the trick is only just you open it once and close this thing, and now it will show 3 bits. So anyway, now let us analyze this code simulation waveform, like whatever operation has happened, right? So here clock is there. So if you observe from this point, let me just draw and show you few things. Okay, just drag this. Okay, so what we'll do is the moment reset comes here, the moment reset comes here, if you observe, the D out becomes 0. This last signal D out becomes 0. And now W underscore I is high. So whenever it is high, at 0 location, you are storing this data. At location 001, we are storing this data. So till the point the W underscore R is high, that is till this point, this entire part is called our write cycle. Because without writing something into the memory, you can't read, right? So for 8 locations from 000 till 111, I am writing different data. And from here, if you observe, W underscore R symbol became low. That is, it became 0 from here. If I click also, you can understand here. So it becomes 0 when I click here. And now if you observe, I am just giving address values, that is 000. So what is the D out I am getting? 111. Because why? Because in address 000, what is the data I stored at that time? 4 ones. So when I am reading and giving that address, I am getting that same data in D out signal, because now I am doing the read operation. And when I give 001 as address, I got 1110. So that same data I am getting now. So like that, I can check for all combinations like 111. That time I wrote 1000. So when I give that data address as 111, I get 1000 as answer in my D out. So one thing what we need to understand in this is there are different operations in memory. Okay. For example, if we take any memory, whenever we are doing write operation, we are writing into the memory. So whenever doing write operation, we need two things. First is address, which tells us where to write. Second is data. It tells us what to write. Address tells us which location we should go. Data tells us at that location what we need to store. So this is our write operation. Second part is read operation, where data is already stored in memory and we are just reading it. This is called read operation. Okay. In read operation, we need only one thing, that is the address. That means you just tell me at which location I should go. I will go to that location and I will bring the contents and I will store it in D out. So these are the two important things in memory operation. And I'll just show you the code once again in a single frame so that you can try it on your own once. This is our design code. Okay. And this is our test bench code. So I will just drop a link of this EDA playground in the description. You can also check out that complete code through that link. Thanks for watching.